So in the last video, we talked about how we see objects, and that what we really see is the light that's reflected off of those objects into our eyes. But some things do actually emit light, right? So for instance, the sun or a light bulb or something like that actually emits light. So when we look at that, it's not the reflected light, it's the actual light that it produces that we see. And when that light hits other objects, we can see those objects by the light that's reflected off of them. And this is actually a really complicated subject, so I'm going to give you a very simplified version. And I'll kind of divide light sources into two different camps. There's incandescent lights, or that produce light through incandescence, and then there's fluorescence, which is another way to produce light. So incandescence, like an incandescent light bulb, produce light through the acceleration of charges, kind of in that very basic way. Like we're accelerating charges, so we're making electromagnetic waves. If you increase the temperature of an object, you're going to increase the frequency of the light that it emits. Don't really ask me why, but that's kind of how it goes. But the general gist of incandescence is that you have these things moving around, and they'll move by each other or they'll run into each other, and that will give them energy. And that energy will be converted into light energy because it'll result in accelerated charges. Okay, so that's the short version of incandescence. Basically, you got things moving around, they hit each other, they transfer energy. Sometimes that energy will result in a charge being accelerated that produces light. Fluorescence is very different. So a fluorescent light bulb, you'll notice, is not hot when you touch it, but an incandescent light bulb is. And again, that's just because you need to get things really hot for them to produce high frequency electromagnetic waves. Fluorescence works on a totally different principle. And to understand fluorescence, we'll introduce the Bohr model. And the Bohr model is just a way of describing an atom. It's not an accurate description of an atom, but it does have some really key components which were really important scientifically. The main one being quantized energy levels. And an energy level is just kind of like a place or an energy that an electron can have. And the weird thing about it is that it's not continuous. So an electron can't have any energy that it wants. There are kind of a few set things that it can do, right? And we often draw these as these kind of like circular orbits around the nucleus. And so you'll see there's one energy level here, a second one, and then the third one. And that the electron can't be in between. It can't be here, it can't be here, it can't be here. It's got to be at this, this, or this. And that's what it means to be quantized, and that they have very specific energies. So if you get an electron, and it's in this, right here, it's in its ground energy level, or the kind of lowest energy level, and you give it energy, and you can give it energy in the form of light. So here, this is just another way of writing E equals h times frequency. So if we send some light at it, and we get this electron to absorb that energy, if the energy is exactly right to get this electron to jump to this energy level, it will do so. If it gets a little too much energy, it would put it out here, and that doesn't really exist. That's not a place that the electron can be, so nothing will happen. If it's not quite enough, it won't go part way there, it just won't go at all. So say we give it energy, we feed it light at the exact right frequency for it to jump from here to here. Now we have what's called an excited electron. And the thing is that these higher energy levels, right, further away from the nucleus, they have more energy. You could see that because it absorbed energy and it got up here. But they're also unstable. So after a while, the electron that's out here will fall back down to a lower energy level just because it's more stable. But by doing so, it'll lose energy. And so to kind of conserve energy, it will emit light, again, at a very specific frequency because it lost energy in a very specific amount between these kind of energies in these two levels. You can see here, this is for a hydrogen atom. Depending on the jump that you have, so if you're going from this high, this fifth energy level down to the second, it'll produce violet light, or you can do the fourth and it'll give you blue, and from the third it'll give you red. And that's why when we excited hydrogen, we saw these three distinct visible bands. Now if you go from 4 or 2, 4, 3, or 2 to 1, it'll produce ultraviolet.